Hello guys, welcome to the Data Structures and Algorithm course brought to you by Asha Akanksha Foundation. So we have learned till recursion till now. In today's lecture we will see the recurrence relations. So let's get started with the lecture. We will first analyze the recursive algorithms we have learned till now. We have already learned to analyze the running time of iterative algorithms considering the number of instructions executed in the word RAM model. In case of recursive algorithms, it is not easy to compute the number of instructions by looking at code. The number of instructions in one instant of function call depends on the number of instructions executed when recursive calls are made. Hence, to analyze recursive algorithms, we require more sophisticated techniques. This is where recurrence relations comes into picture. So we learn about recurrence relation now. A recurrence relation for the sequence an is an equation that expresses the sequence in terms of one or more of the previous terms of the sequence, namely a0, a1, an minus 1. You can see over here for all integers, and this is a very mathematical definition. So a sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. A recurrence relation is just like a PMI, which is principal mathematical induction, which we have learned in class 11th, I guess. So it is basically this expresses an equation in terms of previous terms of that sequence, uh, eh, like we express the kth term in terms of k minus 1 terms. So we can say that in other words, a recurrence relation is like a recursively defined sequence but without specifying any initial values, or you can say initial conditions. Therefore, the same recurrence relation can have multiple solutions because the initial conditions are not unique. But if we set both the initial condition and the recurrence relation, then the sequence can be uniquely determined, and we cannot distinguish between two recurrence relation. So we'll now start with some examples. So take an example that someone deposit rupees 10,000 in a savings account at a bank which gives 5% per annum interest rate with a compound interest which compounds annually. So the my question is how much money would be finally in your account after 30 years? So there is a we can solve this by directly applying the interest formula which we learned in class 9th or 10th, I guess. But we will see how that formula gets derived or how we get to that formula in this example. And this is a part of a recurrence relation because to determine the nth term it uses the n minus 1, or you can say the previous terms. So now we'll now look at this example. So let's consider that Pn denotes the amount in the account after n years, and the n in the subscript denotes that n years. So how can you determine Pn on the basis of the previous years, that is Pn minus 1, that is on the basis of n minus in previous n minus 1 years. So we will now see how can we do that. So we will derive that following recurrence relation, that is, we can easily say that the final amount at the nth year is nothing but 5% is 5% increase in the previous n minus 1 yearth amount, or you can say that Pn minus 1 plus 0.05, that is 5% of the previous years, that is previous Pn minus 1. So it is basically equals to 1.05 Pn minus 1. So if we said that it is given in the question that we have started with rupees 10,000, so P of 0 is equals to 10,000 in this question. So now we'll solve this question step by step. So we can say that P1 is equals to 1.05 of P0, and similarly we can say that amount after second year is equals to 1.05 of the amount in the first year. Or you can say by substituting this equation over here, you can also say that it is equal to 1.05 to the power of 2 or into amount in the starting, that is 0th year from the day we started. We can similarly say that P3 is equals to 1.05 of P2 or we can easily say that which is equals to 1.05 to the power of 3 p naught. So as we go further, the power of 1.05 increase and this p naught remains same. So for the pn, that is amount after nth year, we can easily say that it is equals to 1.05 to the power of n of p naught. So in the last, we are able to determine the amount after nth year in respect of in terms of amount in the previous years. All right. So this is a formula to calculate Pn for any natural number n, and we can avoid the iteration. This is just for your clarification, and we can simply apply this formula over there. So let us apply this formula to find P30 under the initial condition that starting amount, or you can say P naught, is equals to 10,000. So if we directly put on the values, we get P30 is equals to 1.05 to the power of 30 multiplied by 10,000, which is equals to 43,219.42. So we can finally conclude that after 30 years, the final amount in the account would be rupees 43,219.42 rupees. So now let's look at some another example. We have learned in the recursion lecture about the factorial, how we can perform factorial operations using recursion. So if you will recall the factorial function, we have described n factorial as in two terms, like if it is equal to 1, if n is equals to 1 or 0, it, or if it is not 1 or 0, it can be it can be expressed as n into n minus 1 of factorial if n is greater than 1. So we have also derived this recursive algorithm in the previous lecture. You can refer to that. We will give the link in the description. So we have so let's briefly look at the code. We have called the factorial for n, and this is the base condition that if n is equals to 1 or n is equals to 0, we will directly return 1. Otherwise, we return n into factorial of n minus 1, which is this one, and this is the base condition. All right. So let's go ahead. So if we analyze this factorial algorithm, can you please tell me how many multiplications does factorial function perform? If you get the answer, we can say that when n is equals to 1 or n is equals to 0, we don't perform any multiplication, but otherwise we perform one explicitly in the code, and some number of multiplications are performed in the recursive call to factorial of n minus 1. The, Therefore, the number of multiplication can be expressed as a formula similar to the definition of n factorial. That is, we can express the formula for multiplication for the nth term in the terms of n minus 1th term. So we can first of all the base condition, we will see the base condition that if that number of multiplication for 0 is equals to 0, but for the number of multiplication for nth term is nothing but 1, which is this n multiplied by n factorial n minus 1. So we can say that this is equals to number of multiplications for the n minus 1th term. So to know the time complexity of the factorial function, we will have to solve this recurrence relation. So now we will solve this recurrence relation, that is t of n is equals to t of n minus 1 plus 1, given that t of 0 is equals to 0. This is the base conditions. So we have to consider this also. So if we expand this t of n is equals to t n minus 1 plus 1, we can change this n is equals to n minus 1, and we'll get t of n minus 1 is equals to t of n minus 2 plus 1, and we can substitute that this value by the expanded one, which will give us this result. So we can further do this, we can further expand this, and we can say that t of n minus of k plus k is equals to t of n. We are nothing but just describing the nth term in terms of its previous terms. So we will now use the boundary condition that let's assume that t of n minus k is equals to t of 0, which means that n minus k should be equals to 0. That means n is equals to k. So uh, we can easily say that if n is equals to k, it will become t of 0, which we know is equals to 0 plus n, that is equals to n. So we can say that T of n is equals to order of n. That means then multiplications is in order of n. Big O, this is big O notation. We have discussed this also in previous lectures. You can refer to that if you have any doubts regarding big O notation. So we have now seen the factorial algorithm and we have derived the recurrence relation in that. So now we will go ahead and see the recurrence relation for the linear search. So the given problem is that we have given an array containing n elements. We have to search if a value x is present in the array. So we will first learn what is the linear search. So linear search is simply searching for an element in the array, which is basically a order of n. It requires order of n comparisons if we have n elements. So the one part is to examine the first element, which is only one operation, and the other part is to examine remaining elements, which is t to the power of n minus 1 operations. So we'll simply write a recurrence relation for t of n, which is equals to t of n is equals to t of n minus 1 plus 1. 1 for the current operation and n minus 1 for the previous operations. We have solved this recurrence relation previously in the factorial question, so uh, uh, you can pause the video and go in the previous and you can search before. Now we will come to the binary search problem for the recurrence relation. So the problem is you have given an array containing n elements. You have to search if a value of x is present in the array. Binary search. What is binary search? So we will examine the middle element of the array, which is one operation, and then examine either the left half or the right half of the array, and we will go in that particular half, and which only requires t to the power t of n by 2 operations. Thus the recurrence relation for the binary search will look like t of n is equals to t of n by 2 plus 1. So we will search this recurrence relation because we have not solved anything like this. So we can simply say that t of n is equals to t of n by 2 plus 1. We can expand this by putting this value of n as n by 2, and this will become n by 4. So we will put the value of t of n by 2 over here. We'll get t of n by 4 plus 1, and this plus 1 is from here. So so we can expand it further, which will make it t of n by 8 plus 1 plus 2, and we can do that as many times. Let's say we have done it k times, so at the end of the kth expansion we'll get t of n by 2 ki power k plus k. So we'll use the boundary condition now, that is t of 1 is equals to 1. So we will assume that t of n by 2k is equals to 1. That means 2 to the power of k is equals to n. So we will take log on both sides, and we will finally get k is equals to log of n. So if we'll substitute this back in the equation, we will get t of n is equals to t of n by 2 to the power of k plus k. So we can say that t of 1 plus log of n, or you can say t of n is equals to 1 plus log of n, because this is a boundary condition that t of 1 is equals to 1. So we can say easily that t of n is big O log of n. This is just the basic big O notation. If you have any queries, you can refer back to the previous lecture. Now we will see the recurrence relation for selection sort. So the given problem is that we have given an array containing n elements in random order. So we will have to sort it in ascending order. Selection sorter, selection sort. So we'll see what selection sort is. We'll examine the array to locate the smallest element and we'll place it in the first position. This is basically an operation. Now when first element has been sorted, we'll repeat the process for the array containing the remaining n minus 1 element, that is t of n minus 1 operations. Thus the recurrence relation for t of n will look like this. T of n is equals to t of n minus 1 plus n. This is for sorting the first position. So we'll solve this recurrence relation. we can say that T of n is equals to T of n minus 1 plus n. We'll expand it like this, and at the final, the kth expansion, we will get T of n is equals to T of n minus k plus n, and this is a AP series actually, plus n minus 1 plus n minus 2 till we can get n minus k plus 1. So we will use the boundary condition over here that T of n minus k is equals to T of 1, because we know that T of 1 is equals to 1, which is the boundary condition. So we will put n minus k is equals to 1, or you can say k is equals to n minus of 1. So we will substitute this value in the previous equation. We'll get T of n is equals to 1 plus 2 plus 3 till n minus 1 plus n, and this is a simple AP. We'll simply put the formula and get the sum of this AP, which is equals to n into n plus 1 by 2, or you can say n square by 2 plus n by 2, and this is nothing but big O of n square, which is a simple big O notation. So we will now see this how to solve the recurrence relation in the iteration method. So we'll generalize what we are doing till now in a few examples, and we will generalize this in few steps, and you will follow these simple steps to find the time complexity using the recurrence relation. So the steps are: you have to expand the recurrence, and after expanding you have to express the expansion as a summation by plugging the recurrence back into itself until you see a pattern, and after you see the pattern you have to evaluate the summation. uh, in evaluating the summation, these formulas may be used, like for arithmetic series. You have learned in class 10 that sum of AP is equals to n into n plus 1 by 2. Sum of GP is equals to 2 to the power of n minus 1. Sorry, this is GP. So sum of GP is equals to x to the power of n plus 1 minus 1 by x minus 1. These are some specific cases of GP. If we summate 2 to the power of k from k is equals to 0 to n minus 1, we will get 2 to the power of n minus 1. Or if we summate x to the power of k from k equal to 0 to infinity, we will get 1 upon 1 minus x. This is a result if x is less than 1. It is not applicable for x greater than 1. If x is greater than 1, it will tend to infinity. So these are some special cases of geometric series. You can directly remember this, or we can solve this from this formula also. So the other is some other famous series, but not quite oftenly asked questions, is harmonic series. So sum of harmonic series is, as you know, 1 plus 1 by 2 till 1 by n, which is, we can, from Taylor series we can say that, which can be equal to log of natural log of n. So these are some other formulas. You can refer to these, or you can remember this for further recurrence relation problem. Now we will finally analyze the Tower of Hanoi algorithm. This is a very famous algorithm. I will recommend you to first look this algorithm on Geeks for Geeks and understand this, and then come to this part. So this is the code for the Tower of Hanoi problem. So in first you have the base condition, and then you call the Tower of Hanoi from n minus 1 for n minus 1 circles, and then you move the circle from one tower to another tower. This is order of one operation, and then you will recursively call the function for n minus 1 circle disks. So the recurrence relation you can observe from here is something like T of n is equals to 2t of n minus 1. This 2 is because it is recursively called twice in the function. So 2 of t of n minus 1 plus b. This is the order of one operations which is happening in the move function. So if we will expand this recurrence relation, we will get something like this. Expanding further, we will get 2 multiplied by 2t of n minus 2 plus b, and you can solve this and expand it till you see a pattern. So finally we'll get something like 2 to the power of k t of n minus k plus b, something like this. We can we can express this in terms of this also. So the boundary after putting boundary condition that k is equals to n minus 1, we have t of n is equals to 2 p power n minus 1 into t of 1 plus b 2 p power n minus 1 minus 1. So in the final we get something like this: a plus b by 2 into 2 to the power of n minus b. So we can easily say that this is order of 2 to the power n. So we say that the time complexity of tower of Hanoi problem is 2 to the power of n. So I guess you have got a good hold on the concept of recurrence relation. So we'll now end this video, and in the next video we will learn about sorting algorithms and sorting concepts. So if you have any questions regarding this video, you can comment down below if you have any query, or you can reach to us at our Insta and Facebook pages. Hope to see you in the next lectures. Thank you.